My name is Johan Vos, and I'm the author of Quantum Computing for Developers. You can go to the Money website to get this book, and there's a discount code that will give you, I think, 40% discount on this book. I see that the link is behind the camera, but I will show the link more often in this presentation. So, talking about quantum computing, there are lots of questions, and many people heard about quantum computing before, but they have lots of questions because there's a lot information available about quantum computing, lots hyped articles, and lot critical information. So a number of questions are, for example, will it ever become reality, quantum computing, or will it just be something very theoretically? Will it break encryption? That is one of the key things that people talking about quantum computing often talk about, that all the current RSA encryption, for example, will be broken when quantum computers are available. Will it provide insight in the origin of the universe, or more general, will quantum computing be able to solve lots of chemical, biological, physical problems? Will it help in healthcare and so? And will it make existing software developers obsolete? We'll focus on that last question here, and the answer, I can already tell you, is no. So that's what I will try to show in this session. There's a chat in the channel. Yeah, sorry if I'm using the wrong terminology. This is my first ever live streaming on Twitch, so I'm pretty excited about it. Also, very nervous. So you can ask questions, and I'll try to answer them during the presentation, or if they are too hard, I will act as if I didn't understand the question. Oh yeah, so this is not just a slide deck that I have. I'll try to make it a little entertaining, and I will use two games written in Java for explaining some of the concepts. Well, actually, I will use one game, but the game that I will show, which is also part of the book, it's part of chapter 5 in Quantum Computing for Developers. That game is inspired by a game from Stephen Chin, who is with JFrog, and who wrote a game called Mary Had a Little Lambda, I think 8 years ago or so. It's on his GitHub account, so if you want to have a look at that, you can do that. I will just simply launch the game. So there it is. So what we are seeing here is a JavaFX game where we have Mary, the little icon on the left, and this is with sprite avatars. And Mary is walking around, so I'm now using the arrows on my keyboard, and I will let Mary visit the barn. There she goes. Now, when she visits the barn, there will be 3 lamps following her, and that is yeah, well, part of the game. You can wherever she goes, the lamps will follow her. And then there are a number of concepts here. For example, there's the chicken coop here. When she goes there, the lamps change into eggs. So for each lamp, there are 3 eggs. And then when she goes to the nest, the eggs change into chickens. And when she goes to the rainbow, the chickens become colored. Then she can go to church, and some of the chickens are gone and others stay there. She can go to the chicken coop again, where they will become eggs and then go to the nest again. So there will be lots of chickens. And there's a fox as well. And if you go there, boing, all the chickens are eaten. So that is a Java game that was used to explain lambdas, a concept that was introduced in Java many years ago. So the reason I show this is because we will show something similar, but then related to quantum computing. So I'll try not to give a real introduction into quantum computing because that by itself will take more than an hour. And I really want to focus on why quantum computing is relevant for existing and new developers. And I don't think there's another way to start than by comparing quantum computing with classical computing. So in classical computing, we have the concept of a bit. A classical bit is either 0 or 1. And everything in classic computing is based around this concept of bits. We can do operations on bits, and we can concat them in a byte, and we can have a string which is basically a combination of bytes. We can do arithmetic, we can do operations on bytes. In the end, it all comes down on simple operations, gates applied to bits. And for example, probably the simplest operation that you can think of is the not operation, and a not applied to 0 returns 1. In Java, for example, you can see this concept by having a boolean that we assign the initial value of false, and then a second boolean bar is the negation of the first boolean, so that will then be true. So that is very simple how classic computing is working. We have simple bits. In quantum computing, we have also bits, but we call them qubits. They're sort of the equivalent of quantum bits. And similar to classic computing, the operations in quantum computing are done on one or more qubits. So before we are going into more detail about what a qubit is, let's have a look at a game in Java. Oh, and by the way, you can see the URL that will directly lead you to the book on the left-hand side there. So I will now start the Mary Had a Little Qubit game, and we will show some of the code. If you want to see more code, less code, whatever, just let me know on the chat, and I can easily switch between code and slides, or between applications and code. So this is again Mary walking around there. She can still go to the barn, but when she goes there, she will get only one sheep at a time, just to make things easier. And I changed the sprites, or at least the meaning of the different parts in this game. For example, you see at the bottom right that you can press X, H, or C to activate or deactivate gates. These gates are quantum gates. So it's the equivalent of quantum computing, of classical gates, but then applied to quantum computing. For example, when I press the X, you see that the chicken coop is now highlighted. If I press X again, it's disabled, and if I press X again, it's enabled again. So this gate is now active. If Mary walks with the lamp through that gate, you will see that that lamp will change. It's now black and not white anymore. And at the top of the screen, you can see a quantum circuit. You don't need to know anything about that circuit right now. Just be aware of that Mary is now walking with a qubit. So that is a bit. It used to be 0, which is white, and now it is 1. if Mary goes to the church, you see that the value at the church is currently 0. She comes there with a qubit that was in the state 1. So the total value that's now in the church is 1. And we can create a string of 2 qubits, for example. And if we go with those 2 lamp qubits to the chicken coop, they will both become 1. So we now have the representation of 1 1 in binary. 1 1 is the 3 in decimal. So if Mary goes to the church again, the number of our qubit string is read and added to the church. So 1 plus 3 is 4. So that is so far nothing special. That's just that looks like classical computing. The only thing is we do it with qubits instead of bits, but so far there is no difference. So let's go back to the slides. So the qubit that we showed until now is 0 or 1, similar to the classical bit. But a qubit can also be a combination of 0 and 1. And that sounds strange. So how can something be a combination between a combination of 0 and 1? That is counterintuitive. It should be either 0 or 1. As you could see in the game, the lamp was either black or white, but not gray. So how can this be possible with qubits? Now, before we answer that question, let's first think about what is actually a bit and what is a classical bit. And in classic computing, a classical bit is 0 when there's no current allowed, or 1 when there's current flowing through a transistor. So there's a physical component that determines whether a bit is 0 or 1. So there's a direct analogy between the hardware world and the software world. And that is actually the same in quantum computing. There's a direct relation between a physical representation of a qubit and the software representation of our qubit. So we'll first mention a number of possibilities that allow to create a physical qubit, and then I will show how it's represented in software. So physically, a qubit can be a superconducting circuit, or a photon, or a trapped ion, or an electron with a spin. And those representations or concepts that are come from quantum physics that are known to be that can be in a superposition, in a combination of 2 different states. And what is this? Without going into a physical detail, let's take a simple example, of an electron. And you may have heard that an electron has a property which is called a spin. And the spin can be up or down, and it's related to how the electron is moving. And in a spin up corresponds, for example, with the number 1, and a spin down corresponds with the number 0. So if the electron is in spin up, that is actually sort of a qubit with a value 1, and if an electron is in spin down, that is then a qubit in with value 0. But the spin can, the electron state can be in a combination of spin up and spin down, and that means that until we measure the value of the spin, there's a chance that we will measure spin up, and there's a chance that we will measure spin down. And this is really one of the core concepts of quantum physics. This is not. This does not mean that it's either spin up or spin down and we simply don't know it yet. No, it's proven that this is really a combination of 2 spins. And I have to be careful about the wording because some people are very picky about how you call this, but sometimes it's said that this electron has spin up and spin down at the same moment. There's discussion about whether you should use that term or not, but I often think that for developers, you don't need to worry too much about the physical background. So if you want to think about it, that this electron has spin up and spin down at the same moment, then I think that's fine. But the terminology that we're using for this is that this is in the superposition state. A superposition means that we have a combination of two base states here. So it's 1 and 0 at the same moment. Maybe there's at this picture, for example, you can see that there the arrow going up is larger than the arrow going down. So maybe if we measure it, we might have maybe 70% chance to measure 1 and 30% chance to measure 0. But until we measure it, it's both. So there are a number of different possibilities for representing a qubit in hardware. Trapped ions, electron with a spin, superconducting circuit, for example, with Josephson junctions. In the software world, we simply call that a qubit. And I'm very glad to be in the software because I really think that the hardware is really the amazing part, because realizing a quantum hardware is extremely difficult, and in software we can make abstraction of this. We simply assume that it's there, and it's up to the hardware engineers to to bring it there, but that's an incredible achievement that they are doing. So what is the current state of quantum software? Well, you can't buy a quantum computer from Dell at the moment, or you can't go to a Radio Shack or and buy a quantum mobile device or so. So those quantum computers are not widely available. There are some prototypes, there are some commercial implementations for dedicated usage or more general usage. For example, companies like IBM, Rigetti, D-Wave, they have those, and they provide access to those quantum computers, and often this access is provided via the cloud. So you can subscribe to a cloud service, and then you send an application to the cloud, and that's then executed on one of the quantum computers in the cloud. That is not very easy for developers. If you have to test your application by sending the execution request to a cloud service, where you have to wait until one is available, and so that doesn't really scale. It reminds me of when I was a student, that we had a mainframe, and you could write your program and then submit it to the mainframe, and wait for the result to come back the next day or so. The good thing about that was that you were forced to think very hard about your application, because if the debug cycle takes 1 day, you have to think very hard about before you submit a request. But fortunately, the situation now is different, because you don't need to use a real quantum computer to write and test quantum software, because the quantum hardware can be simulated in software. There are some restrictions, because the software simulation is much slower than the real hardware, but that's typically okay, because most of the work that's currently being done with quantum computing is related to experiments and trying to find out which algorithms would be really beneficial for quantum computing. So it also allows you to program in a more higher level language like Java or Python, for example, instead of going low level and talk about the quantum gates which are more complex. It's a bit like in classical computing, you program in a high-level language and not really in machine language. So one of the quantum software simulators that you can use is Strange, which is a quantum computing simulator written in Java, where I'm the lead developer for. And it contains of actually two layers. So the top layer provides quantum APIs at a high level, and they are accessible to Java developers, and you don't need to know much about quantum computing. It's just that they will internally use lower level quantum properties and quantum algorithms to achieve the result. And that lower level is then also accessible for developers. So if you want to use that lower level, you can do that by programming to the lower level APIs. And with Strange, you can currently execute your applications on your own local host, on your own laptop or desktop. And you can also, and that's what I'm working on right now, use a cloud-based simulator. One of the reasons for this is that, as I said, a quantum simulator is slower, requires more memory. So for bigger tasks, it's often beneficial to offload them to a cloud. So comparing the high-level APIs and the low-level APIs, the high-level API is, well, one of the examples is a function called random bit, and that will give you a random bit. So that doesn't sound very useful, but it's very good to as an introduction into quantum computing. And the key point here is that we only use Java types here. So this function has no parameter, but it returns an int, which is known to Java developers. Another function that's part of this high-level quantum APIs is a search function, where you provide a list of elements that you want to search into, and then a function that returns the element that you're actually be searching for. And this is an implementation of Grover's algorithm, which which allows for searching a list leveraging quantum properties, which will make it much faster than if you would have to iterate over all the elements in doing it in a classical way. But you don't need to know anything about how it is actually done, because everything that you see here, this parameters that are passed to the function, are purely Java parameters, existing parameters. So a list, a function, an integer, that's all standard Java. So you don't need to know anything about quantum computing if you want to leverage quantum computing. However, it helps and it's fun. The main reason why it helps is it's good to understand why some algorithms are applicable to quantum computing and why others are less applicable. And at a low level, the low level API in Strange is using gates like the Hadamard gate. I will come to that immediately, or the X gate, which is the NOT gate, or the conditional NOT gate, and that uses quantum types. And if you want to use this API, then you need to know what you're doing. Strange, so that quantum simulator is an open source project. You can go to GitHub, RedFX Quantum Strange, and you can find the source code there, and it contains some information about how to build it if you would like to build it, and how to run some samples. So, well, maybe I can quickly show the website. So this is Strange. It explains how you can get started with a very simple program. So this is how you can use Strange. you create, this is a simple Java application, so developers familiar with Java will immediately see that this is really the Java that they're used to. And you can create a program, a quantum program, add some steps and add some gates to those steps, and then execute the program and measure the result. So this is using the low-level quantum APIs. We will use the high-level, or I will at least show the high-level quantum APIs as well. Well, actually, I can show them right now. I open NetBeans, and there you see the code of Strange. So this is the Strange project loaded in my IDE, and there's a call a class Classic, which provides some of the high-level APIs. And so the method that I showed on the slide is the random bit method. It returns an int. It returns a random number. So that's actually the first use case that I describe in the book. How can you return a random integer in Java with quantum computing? That sounds totally unuseful, but actually it's not, because this is really, if you apply this to real hardware, this is really a purely random as it can be, at least with our current understanding of quantum physics. And that is useful in security and so on. The implementation of this method is using the low-level APIs, as I said before. So in this implementation, we will use things like a program, like a step, Hadamard, which is one of the gates in quantum computing. So this is really doing the real quantum work. It will do this in a quantum execution environment, which is just an interface. Well, while I'm here, I can probably show this interface, which allows you to run a program, and a program is then a quantum program. The simple quantum computing execution interface that we're using here is simply using your local host, but the same application that you are using, that you're writing, can also use, for example, a cloud quantum computing execution environment. And it would be nice that in the future, when there's real quantum hardware, that you can keep your programs and you just change the quantum execution environment to real hardware or so. That is not for tomorrow, but that doesn't matter too much to you as a developer, because think about, I often compare it with the Y2K bug, the Millennium bug. We knew that at the year 2000 that some of the existing computer software would stop working because of well, issues with how the date was stored. And it took a long time before all the software was updated, and you didn't want to wait until it was really 2000 before you started working on it. So therefore, it's very useful to start working with simulators before real quantum hardware is there, because then by the time that quantum hardware is available, you will have your applications ready. So going back to what a qubit actually was, so we said that it can be, the physical representation of the qubit can be spin up, spin down, or a superposition of up and down. And in hardware, it is possible to bring to realize superposition in general. For example, with lasers, those can be used to get trapped ions in superposition. It's and this is really mind-boggling technology, but it's not science fiction. So this really exists. So there are quantum computers with 5 or 54 or even 70 qubits, and so it's the different technologies that are making up quantum computing are working and are being used already. So That's not science fiction. In software, we do it much simpler. We apply gates. So let's show what this 1 and 0 at the same time means at the software concept. So we go back to the Mary had a little qubit sample. And we will let Mary walk again. She will go through the barn where there's a lamp. And I will now press the H to activate the nest. This H is now a Hadamard gate, and a Hadamard gate will bring a qubit in a superposition. So this qubit, or this lamp with the number index 0, is currently holding the value 0. You see that because it's white. But by visiting this Hadamard gate, and you will see that when the lamp enters the Hadamard gate, it's now changing colors. So it's sometimes 0 and it's sometimes 1. And that is our representation to show that this is in a superposition. So we don't know if it's 0 or 1. It's actually both. So it could have been gray, but I think it's more fun to make it well, blinking a bit. So when Mary now goes to the church, at that moment the qubits are red, and the value that we read is added to the value in the church there, and the value is 0. So that means that at the moment that the measurement was done, the qubit was was measured 0. So let's do that again, but this time we create 2 qubits, and well, actually, let's make it a bit more complex. We create 3 qubits, and we will send all of those through a Hadamard gate, and that means that all these qubits are now in a superposition of 0 and 1. So, and you see they are individually alternating between 0 and 1 with a random interval. And if we now go to the church again, they are all red, and the value is now 7. So that 7 is actually 4 plus 2 plus 1. So that means that all of the qubits appear to be 1. That's purely coincidence. If we would do it again, we could have 7 again, or it could be 1 because it was 0, 0, 1. So that is how actually a random number work in quantum computing. So what you've actually seen here is a visual way of explaining how that random bit algorithm worked that we showed before. And let's close this and go back to the well, maybe I can first show how it's how it works in Mary had a little qubit. This is part of the code of the game that we show. So there's the @h method, and whenever a lamp enters the nest, so when the lamp passes over that nest, then we add a gate to the qubit, and this is a Hadamard gate. And the Hadamard gate is a special gate that brings a qubit in a superposition. So the NOT gate that we showed before, which was represented by the chicken coop, will simply flip the value. So if it was 0, it would be 1, and if it was 1, it would be 0. So that was the other gate. But the Hadamard gate that we are now using is bringing a qubit in a superposition, and we add that then to the program. And that actually looks very similar to the implementation of the random bit method that is part of the top-level API of Strange. So because what we do here is we create a quantum program with a single step, and in that single step we apply a Hadamard gate to the qubit that's part of that quantum program, and we execute that program. When we measure it, we will measure one of the possible values. possible values, that is very important, and that is part of where quantum computing gets its strength from. Typically, I start presentations with explaining why quantum computing is so powerful and relevant, but I wanted to try it in a different way now by first explaining the concepts. It might be easier to understand why it's so powerful. So we explained that with one qubit, we have two possible options. So it can be 0, a qubit can be 0, or a qubit can be 1. And it can be in a combination of 0 and 1. So we actually need two values to know the state of that qubit. If we have two qubits, there are in total 4 different options that this system can be into. It can be in a 0, 0, 0, 1, 1, 0, 1, 1 state. And if we have 3 qubits, there are 8 options. And if we have n qubit, there are 2 to the power n options. So, and that is very different from traditional bits, because if we have 3 bits, they can be in one single state at the same time. And a quantum system with 3 qubits can be in 8 states at the same time. So, and that is so that means that the total number of combinations grows exponentially with the number of qubits. And yeah, it's a bit sad that when I started writing this book, not many people, well, I had to explain the concept of exponential behavior of functions, but today with the coronavirus, it's more people know about exponential behavior, and where with corona it's working against us. In quantum computing, it's working with us, because the more qubits we have, we will have exponentially more combinations that we can process at once. And if you look at this graph, for example, on the x axis, we can have the typical size of a problem that we need to solve. And on the y-axis, we see how many combinations that we can test per second. And then you see that especially the bigger the problem become, the more the advantage of quantum computing becomes prominent. So that is one of the key things about quantum computing, that for bigger problems that are almost impossible to tackle with classical computing, quantum computing can provide an answer. And there, the so often called quantum computing will break encryption is relevant, because the current encryption techniques that are based on integer factorization are sort of proven to be unbreakable by the current classical computer capacity. But with quantum computers, there exists an algorithm that can do this in polynomial time. So if you add more bits to the secret key, it will become exponentially more difficult to fix that with a classical computer, but it will be just a bit more difficult with a quantum computer. So that behavior of quantum computers, where where you can hold different values at the same time, makes them very suitable for complex problems. I have to be honest about this. And actually, I only added this slide last minute because I sometimes want to skip this, because I do realize that this is sometimes confusing, and therefore in the book I really build it up from chapter 0 to chapter 1 to 5, and it's a disillusion to many when they hear that. Well, you might think that, okay, we can get 0 and 1 at the same time. So if I have 2 qubits, I can have 4 values at the same time. But then you hear that when you measure it, you will measure only one value, because whenever a qubit is measured, it will be either in the 0 state or the 1 state. So that sounds like a cheap magic trick, where I say that this is 0 and 1, and when you look at it, it's either 0 or 1, but then you won't believe me that it used to be 0 and 1 at the same time, but really it is 0 and 1 at the same during the processing. So that is something that there's no doubt about. But the question that I often get is, why is this then useful if we have, for example, a 3-qubit system with 8 options? In the end, there will be only one measurement that I can do. So why is this better than classical computing? Because with classical computing, I can do one measurement as well. Well, in a system with 6 qubits, for example, we have 64 probabilities. But when we do a measurement, we will go back to a single result. But the secret is in the processing. In a classical computer, during processing, the let's call it the register, which contains a number of bits, can hold only a single value at the same moment. But in a quantum computer, those registers can hold 2 to the power 6 values at the same moment. So to simplify things a bit, you can process 64 values at the same time. So you need only one processing step to process all 64 possibilities. And I sometimes compare this with the Stream API in Java. You can use parallel streams and you get a parallel part for free with a quantum computer, because the quantum computer will do everything in parallel. And okay, the result is just a single number, but what if your problem is you're given a list or with 64 values, and you're asked, what is the biggest number in this list? Well, the result is only one number, namely the biggest number. So you don't need 64 outcomes. You just need one number, but you need to process all those numbers. But that processing can be done in parallel on a quantum computing. And the goal is then that your quantum algorithm will use the correct gates so that the algorithm will return the biggest number. There's one other quantum physical concept that we have to talk about, which is quantum entanglement. And that is even weirder than superposition. It's something that even Einstein didn't really believe in because it was so strange. But I'm not going to go into the physical details about this, but 2 qubits, so the physical representation of 2 qubits, can be entangled, which means that even if they are in a superposition, so they are both 0 and 1, and they can be miles away from each other. They can be literally at the opposite corners if there would be a corner in the universe. If you measure one of them, you immediately know the value of the other one. And if there are, so if you measure one of the, if 2 electrons would be entangled, and you measure one and you measure spin up, then you know that the other one has spin up as well. Well, depending on how the entanglement was created. At least there's 100% certainty, even if they are very far away. Even the information, the measurements will be related to each other, and that is very interesting, because the even if they are 10 light years away, the measurements are if you measure them at exactly the same moment, they will be the same. So that's the reason why Einstein and others had issues with it, because that sound like information can travel faster than light, which is by definition impossible. There's now an interpretation on how this is still not conflicting with the absolute speed of light. So it's proven that this is true as well, and it's proven to be useful in quantum computing. So let's show what it actually means in the quantum algorithm. So the Mary had a little qubit is simply using the strange APIs, in case that wasn't clear yet. So starting that, Mary had a little qubit again. Oh, by the way, if you have questions, feel free to ask them in the chat, and I'll keep an eye on them. So we will have Mary visit the barn twice again. So we will have a quantum system with two qubits, and we will activate the nest. So this is now an active Hadamard gate. And when the first qubit or lamp visit the gate is active. So you see it's alternating between black and white. So it is in a superposition. We now deactivate the Hadamard gate, so it's not highlighted anymore. So I pressed the H, and we let the second lamp pass through it, but that stays white, so that's not in a superposition. You can actually see this on the on the qubit representation. So at the top of the screen, you see the first qubit, qubit 0, which corresponds to this lamp, is has been applied a Hadamard gate, and you can also see on the right hand side that there's now 50% chance that if we would measure this, that it will read as 1, and 50% that it would read as 0. And the second qubit has no gate applied, so it is off, so that means it will be measured as 0. But now we have a different gate, the C0 gate, which is the rainbow here. I can activate it by pressing C, and then the C0 gate is activated. You see the rainbow is highlighted now, and Mary travels with both qubits to that C0 gate. And let's see what happens then. Well, a number of things happened. So first of all, we see that here is a link created between the two qubits, and those two qubits are now in an entangled state. And you see that they are now both in a superposition, because they are both black and white at the same moment. But we don't know if they are 0 or 1. They are both having an equal chance of being 0 and an equal chance of being 1. So let's go to the church, which means we are measuring the qubits, and let's see what value that we will measure. And well, it's easy to first measure and then explain what we will measure, but let's do it differently. Actually, there are two possible values that we can measure, and if someone wants to guess, you're welcome to type it in the chat. I will keep talking while people can think a bit about it. But so there's a possibility that the two lamps are in the 0 state, that they are white, and in that case we will measure 0. There's a possibility that they are both in the 1 state, and in that case we will measure 1, 1, which is the binary equivalent of 3 in decimal. So in that case we will measure 3. There is no possibility that the first one is 0 and the second 1. And there's no possibility that the first one is 1 and the second is 0, because those qubits are entangled. So whatever we will measure here, I guarantee you that it's not going to be 0 or, it's not going to be 1 or 2. So because 0, 1 is the binary equivalent of 1, and 1, 0 is the binary equivalent of 2. We cannot measure those states. And that's interesting, because if you look at the possible, my camera is before the possible outcome, so let's move this a bit. And well, you see here now that that there's a 50% chance that we will measure 0 when we measure the first qubit, and there's a 50% chance that we will measure 1 when we measure the second qubit. But based on this entangled states, they will be the same value. So the only possible measurements are 0 or 3. So let's see. And we measured 3. So that actually means that both qubits were, when measured, in the one state. So whenever you do this again, it will be impossible to measure 1 or 2. So let's just do this again for fun. By the way, so you can download this code and you can play for yourself. You can examine the code and the details and modify it and play. So we will create this entangled state again by first applying a Hadamard gate, bringing the first qubit in a superposition, and then is the CNOT gate is now activated. So this gate is being applied to the two qubits, and we will now add the value that we will measure to this 3. So again, we will either measure 0 or 3. So the result will be 3 or 6. It will not be 4 or 5 unless there's a bug. And again, yeah, the value is 3, which is yeah, there was 50% chance that we would measure 3 and 50% chance that we would measure 0. I can keep going on with this, but I really have no influence on the algorithm. So it can be 3 again, but let's do it one more time. And let's, well, maybe hope that we will now measure 0 so that we will stick with 6. There we go. And yeah, that's a coincidence, but this time we measured 0. So no, both qubits were in the state 0. So that's an interesting concept. Let's maybe have a quick look at some the code. The CNOT gate, which is actually the rainbow that we showed in the game, is a gate that's being applied to 2 qubits, and that will bring those qubits that will well, if one of the qubits went to a Hadamard gate before, then applying the CNOT gate will bring them in a in an entangled state. Again, this is something that you don't need to know as a developer, but the algorithms that you are using will use it. For example, let's there's an algorithm that measures the period of functions, which is used in Shor's algorithm to factor integers, and that is making extensive usage of different gates, and that looks a bit complex, and it actually is extremely complex. So if you want to look into the details, you're very welcome to do so, and this is also explained in the book. This is actually in the last chapter. But if you are not interested in the details and you just want to factor an integer into its prime numbers, then you can simply call the qfactor method, which is a purely Java method, which is implemented using quantum computing under the hood, but you don't need to know it. It's important, though, that you realize that not every algorithm is applicable to quantum speedup, and quantum computing is not going to be used everywhere. For example, for creating user interfaces, I don't see immediate benefits for it. It's really for hard mathematical problems, or problems that can benefit from clever mathematical algorithms. And this is often the case in security, artificial intelligence, medical software, image recognition, and actually physics itself, because if we want to simulate, if we want to study nature, then it helps using the technologies that nature is using, and that's not classic computing. So I actually already showed the code. I showed a JavaFX application using strange, because the Mario had a little qubit is a JavaFX application using strange, and I showed some of the quantum algorithms that are that you can use in strange if you want to develop um, using quantum algorithms. So if you want to learn more about it, you can of course go to the strange website, or you can look at the samples. I will give a link immediately. But before we wrap up, let's look at the I think the two important conclusions and takeaways for developers are, first of all, quantum computing is very different from classical computing. There are some properties in quantum physics that make it very interesting to do some things with quantum computing rather than classical computing. And those properties, I covered the two important properties here: superposition and entanglement. Superposition, which allows a qubit to have more than one value simultaneously, which allows for exponential speed up, and entanglement, which allows a combination between two properties. That is, and it would really require another session. That is something that's very interesting in secure quantum key distribution, for example. So if you want to make sure that nobody tampered with your keys, then entanglement is really helpful there. And there are some libraries, like for example, if IBM has a QuizKit, for example, which is a Python library, excellent if you're a Python developer. If you're a Java developer, Strange is a library that I can highly recommend. And with those libraries, software developers can today write applications that leverage quantum computing without having to be you don't need a PhD in quantum physics, and you don't need to know the underlying principles of quantum computing or the or quantum physics. As I said before, it helps to have a high-level understanding of what is actually happening under the hood, because that will give you a better insight of, yeah, this might be a problem where quantum computing might be beneficial or not. So and the relevance for this is that you can do this now already on existing simulators, and the algorithms that you are using or developing will later then work on real quantum hardware. So that actually concludes my presentation. You can, you know what, I will change this slide a bit real time so that that link is visible even if my camera is in front of that. There you go. So yeah, thanks for attending my first ever live stream. If there are questions, I'm happy to take them. You can also follow me on Twitter and contact me there. You can have a look at Strange, which is the simulator in Java. You can create issues for it. You can cooperate with it by writing pull requests. And the samples that I'm describing in this book are available on my GitHub repository, Quantum Java. So if you want to get started with some quantum applications, that is probably a good starting point. And all the samples are explained in the book, of course. So thanks for watching, and I hope that you're at least a bit enthusiastic now about quantum computing. It's going to be very interesting to see how it's going to change the world, not only the IT world, but also society in general. Thanks for attending.